Okay, so we're looking at eigenvalue problems. Just a quick overview. Last time we covered social network graphs. We talked about betweenness as a measure of detecting communities and to partition graphs. We specifically looked at the Gervan-Newman algorithm. Towards the second half of the lecture, we also focused on computing the graph Laplacian. And then we focused a little bit on the spectral bisection, which is basically to use the Fiedler eigenvalue and the Fiedler eigenvector, which is the second smallest eigenvalue eigenvector, to partition a graph. Of course, that raised the question of how do you actually compute the particular eigenvalue, the second smallest eigenvalue, or the eigenvector. And so there are many ways of doing it. I'm just going to cover the main mathematical background on how you go about doing this. Okay? So let's sort of start. We're going to have a small deviation. Conceptually, when we think about eigenvalues and eigenvectors of a particular matrix, think of taking some arbitrary vector. An arbitrary vector, when the matrix is applied to it, basically, which means that you take the matrix and you compute the product with this vector, it's going to transform this vector in some sense. So if you think of the matrix A as a transformation, then whenever this vector is aligned with one of the eigenvectors, it's going to scale or shrink it in that direction. Of course, when it's in a combination of it, individually along each of those dimensions, they're going to be scaled and stretched. The amount of stretching or scaling is going to be decided by the eigenvalue corresponding to that eigenvector. So you can think of this matrix A, which does some complex operations given a vector, and the eigenproblem or the eigendecomposition just gives it to you or separates it out into more meaningful ways. So think of it intuitively like that. There is this complex interaction, and we are just breaking it up into these orthogonal vectors, and the eigenvalues give you the scale or the relative influence of each of those vectors. There is another way to look at it, at a more fundamental mathematical way, which is that if you look at the equality that we had, which is ax equal to lambda x, we could write it more like an equation of this sort, which is a minus lambda I times x equal to 0. And we can solve this, right? You can think of a minus lambda I as being another matrix P. So you're solving an equation with a 0 right-hand side. More specifically, we also have something known as the characteristic polynomial. Student is not here, but some people, if you have a small enough system, if the matrix A was small enough, you could actually solve it analytically for the eigenvalues and the eigenvectors. And typically, for those of you who might be doing some imaging or robotics, you might get 2x2 and 3x3 matrices. And there you can actually compute the analytical eigenvalues and the analytical eigenvectors. But specifically, the eigenvalues of the matrix are the roots of a polynomial equation, which is given by the determinant of a minus lambda I. It's a polynomial. Yes?
I is
identity. It's an identity matrix. So if you look at this equation, I've just rearranged it. If I take lambda x onto the left-hand side, right? And because I want to combine it with a matrix A, and lambda is a scalar here, right? So I want to multiply it with an identity matrix so that I can stack it together with the matrix, right? That's all we're doing. And in this case, so if you look at the characteristic polynomial, you're going to get a polynomial equation. If you treat lambda as a variable, it's going to be an nth order polynomial function out here. And so the roots of that polynomial equation are going to be your eigenvalues. Of course, if n is very large, you don't want to solve it. If it's a quadratic equation or a cubic equation, you might be interested in solving it. So if you think of it as an exercise, you guys might want to consider a 2x2 matrix and compute its eigenvectors or eigenvalues analytically. Again, keep in mind that
you get the eigenvalue. How do you calculate the eigenvector?
once you have it, you can plug it back into the equation and get it. So primarily, you will just do this. we'll keep coming back to all of these different scenarios. The characteristic polynomial is a powerful theoretical tool. If you want to look at theoretical concepts, if you want to get analytical expressions out, it's nice, but it's not very useful computationally. So we'll skip it, but it's important for you guys to, and for the purposes of completeness of this lecture, I'm going to cover a few topics which you're not going to use. Let's look at the considerations. Just for a minute before I get into it, because like I said, this is not a full, this is like 2 or 3 math lectures squeezed into one. So few things that we'd like to focus on, right? Now, of course, the properties of the eigenvalue problem affecting the choice of the algorithm, right? So these are the issues that we might want to consider to decide how we want to solve it. The first question is, do we need all the eigenvalues or only some of them, right? If you only want, say, the largest, or in the case of the spectral bisection, we only needed the second smallest eigenvalue. So that's going to change it. If you have a very large n by n matrix, then those algorithms which allow you to target specific eigenvalues are important. Second question is that, do we only need the eigenvalues, or do we also need the eigenvectors, right? So that's also going to affect, and we'll see that there are some cases where getting the eigenvalues is much easy, whereas getting the eigenvectors requires a little bit extra effort beyond that. Of course, the kind of the matrix makes a difference. I'm going to keep the rest of the talk fairly generic. We'll focus on some of them. Are they real or complex? In most cases, this doesn't affect us too much. So I have always used the convention of sticking to the complex, the Hermitian conjugate instead of the transpose, but you can ignore that for now. Is the matrix small and dense, or is it large and sparse? How that affects is are you going to use factorizations? Are you going to rely on approaches which use matrix vector products? Towards the end, that's what we're going to look at, specifically the Krylov subspace methods. And of course, does it have any special properties such as symmetry? Symmetry especially is important when you're solving eigenvalue problems, because it really reduces the cost and the computational complexity of solving our system. It also reduces the storage cost required. So these are some of the things that we're going to look at. Now, as we look to solve these problems, if you look at it, if you start searching online or even in your literature, in your textbooks, you'll find a few hundred different methods for solving your eigenvalue problems. These are very fundamental problems. That's why it's called the eigenproblem, the first problem. But fundamentally, the ideas surrounding how most of these approaches work are very simple. And that's what I'm going to summarize. And as we step through this, you'll see the method come out till we reach the power iteration method, which is what we have already seen when we did the PageRank algorithm. Okay? But fundamentally, the ideas behind almost all the approaches are based on a few basic concepts. Okay? So let's look at it, and please understand, especially if you get anything else from this lecture or not, try to understand the next 2 or 3 slides. Okay? So let's look at some properties, which is basically transformations to our eigenproblem, which is going to allow us to work around some of these constraints that we have. So the first is the shift. The first 2 are very important because we'll be using them through this lecture. The other 2 are important for you to understand. We won't really be using them in this lecture. The first is the shift, which is that if you have an eigenvalue problem of the sort ax equal to lambda x, and sigma is some scalar value, then alpha minus sigma identity x is equal to lambda minus sigma, which means that a shift of sigma in the original matrix gives you a shift in the eigenvalues of the resulting system. Is this clear? What it means? So if you, yes? Exactly, that's all. But you need to, none of this is these are mostly very trivial. These are going to pop out immediately. You can actually go through all of them, and it's going to be very, very simple for you to see. So, all I'm doing is that if you expand that, it's alpha x minus sigma x is equal to lambda x minus sigma x. You just strike these off, you return the original one, okay? So, but we're going to be using this. Why are we going to use this? We're going to be using it because if you remember from our PageRank example, we could mostly target the largest eigenvalue. If you want to target eigenvalues at a different level, then we want to be able to use shifts to do that. Okay? We'll formalize that in a minute. The second is inversion. Okay? If A is non-singular, and given the same problem, Ax equal to lambda x, as it's non-singular, then lambda is not equal to 0, and A inverse of x, right? I'm going to write it as x by A is equal to x by lambda, which basically is coming straight away from this. The non-singularity just makes sure that I can compute the inverse of A, right? So this is all we are doing. Why is this important conceptually from an eigenvalue perspective? No, the reason is that the power method, which we've looked at before, targets the largest eigenvalue. So if you want to estimate the smallest eigenvalue, we talked about that for the spectral bisection case, we want the second smallest, you can do something like this, which is that you estimate the eigenvalues of the inverse. The largest eigenvalue of the inverse of A inverse is basically going to be the reciprocal of the smallest eigenvalue of A. So by doing this, we can get now the smallest eigenvalue of a given matrix. Okay? The powers comes directly from that, which is basically you can just break it up into, and so on. You can recurse it. The final one is the polynomial. Like I said, we won't be using this, but polynomial is simple because you would just expand the polynomial and write it in terms of powers of A, and so the equivalence is there. So these are important properties which allow us to manipulate the problem at hand to get the values that we are interested in. Okay? This is one of the most important concepts. Most of the algorithms tackling eigenvalue problems make use of these kind of approaches, and that's known as a similarity transform. Okay? If B is similar to A, if there is a non-singular matrix T such that B is given by this similarity transform, which is T inverse A T transpose. Okay? So assume that given a matrix A, I can create a matrix B using these transforms T. Okay? Where T is non-singular because we need T inverse there. Then follow this expansion. Basically, we are interested in the eigenvalues and the eigenvectors of B now, right? By expanding B in terms of A as T inverse AT equal to lambda y, we see that A T of y is equal to lambda T of y. What does that tell us? Focus on this expansion. Is this expansion clear? How we went from by equal to lambda y to aty equal to lambda ty?
Find the eigenvalues of B.
No. Forget finding anything right now.
Okay.
What does this tell you? It tells you that the eigenvalues of B are the same as the eigenvalues of A. Please make sure you understand this, because this would be one concept I want you to take home at the end of the day. Right? Do you see why the eigenvalues are the same? Replace Ty by Z. Right? So if I replace Ty by Z, what do I get? Right? What does this tell you? That lambda, which we started off, if you remember, was an eigenvalue of B, correct? Is it clear? So, as long as we have that sort of a transformation, then the eigenvalues of this new matrix B are the same as the original matrix A. And what can you say about the eigenvectors? What can you say about the eigenvectors? I mean, it's easily good, it's here. What are the eigenvectors of, okay, what is the eigenvector of B here? Y, right? What is the eigenvector of the original matrix Ty, right? So what this says is, and that's why I'm focusing on this slide, the general approach to solving an eigenvalue problem given an arbitrary matrix is to figure out a transformation of this sort. You figure out a transformation, which is basically a similarity transform, and you get a new matrix B. This matrix B possesses certain properties which make it easy for us to eventually compute its eigenvalues and eigenvectors. Okay? So you do it in two steps. In the first case, you figure out a similarity transform, and most algorithms are going to differ on how you're going to find this. Once you have found such a transform and you have this matrix B, which I'll show you what kind of properties make it easy for us, we will compute its eigenvalues and eigenvectors. The eigenvalues are the same as those for the original matrix, and the eigenvectors can be easily obtained by applying the original transform onto the eigenvectors of P.
It's inverse, right? Not transpose.
Sorry?
It's T inverse, right?
Here? Yes.
Okay.
In this case it is.
Okay.
So that's what we are looking at. Okay? Is this clear? Do you see?
B, A need not be a singular matrix in this case.
A need not be. So we are making that's why we are making this approximation. Because B will mimic the structure. So if A is singular, then B is going to have singular, because by this definition, A and B have the same eigenvalues.
Yeah.
So if A is singular and has 0 eigenvalues, then you're going to have B is going to.
In some sense, we are only rotating it. We are making sure it's.
And we'll see why. So here's the question.
Yeah, but still, that's what I wanted to say. So let's say that matrix A is some kind of transformation.
Yes.
So what T does basically takes the input, which is some vector, and transforms it into the space where A works. Then you apply the A transformation. Then you transform it back into the original space where B works. And then that's why B equals to that. So that's why the singular variables are of course equal. Everything, it's basically the same matrix, just different bases.
Yes. We are going to look at some cases where there will be approximations as well. Typically, when we do it, eventually towards the end of the day, you will see that you can eventually get to this. But if you have iterative approaches where you are progressively updating both T and B, these are the methods that we talked about. This is what I'm eventually getting at. When we look at your Krylov subspace methods, you're iterating and you're getting close to the solution. But the approximation that you get for B, and again, if you think spectrally, most of your iterative methods are going to converge close enough to the largest and the smallest eigenvalues. So if you're only interested in those, you could stop with approximation. For now, focus on this. Okay? Is everybody clear with this? The general idea behind it. So the general idea, I'm going to repeat again. Find a transformation so that we can get a matrix B, a similarity transform, so that we can get a matrix B which has special properties, which make it easy for us to get its eigenvalues and eigenvectors. And once we have those, basically the eigenvalues and the eigenvectors of B, we can easily get the eigenvectors of A as well. And the eigenvalues are the same. So now let's look at cases where it's easy to compute the eigenvalues and the eigenvectors. The easiest is the diagonal form. So if you have a diagonal matrix, what are the eigenvalues? The eigenvalues, right? What are the eigenvectors? It's there on the slide, but yes, it's just the columns of the eigen, right? Of the identity matrix. So if we can, by a similarity transform, take a matrix A and transform it in this fashion so that matrix B ends up being the diagonal, then it's trivial, right? Because you convert it into a diagonal matrix, you're basically getting your eigenvalues, and the transformation that you did, because that's going to be applied to the identity matrix, are basically your eigenvectors. Okay? So that's going to be easy. Of course, it's not easy to diagonalize every single matrix. So, and it's actually not even possible in many cases for us to diagonalize. So what we end up with more commonly is in converting our matrix to a triangular form. Okay? This is possible for any matrix. And you can look into it, and there are proofs which will that you can convert, you can transform any of these The eigenvalues are simply the diagonal values in this case. So if you have a upper or a lower triangular matrix, the eigenvalues are very easy. And this goes back to what I said at the beginning. If your motivation is only to find the eigenvalues, then you can stop here, because you can just, at the moment you convert it into a triangular form, you extract its eigenvalues.
You mean that this is the Jordan form?
This is not the Jordan form. The Jordan form is
An instance of
yes. It's the Jordan form usually gets compared. It's the closest for matrices which cannot be diagonalized.
Yes.
That will be the closest you can get to being.
That's where we put the eigenvalues.
Sure. Yes. I am skipping. I'm avoiding as many concepts here as possible. My goal is to get to the iterative methods out here. But yes, you are eventually going to. So I'm skipping the proof in this case of the fact that you can. Let's just say that you can convert it. The eigenvectors are not immediately obvious on how you would extract it, but with simple work, they can be extracted. And we'll look a little bit at this. The power iteration itself. So instead of doing something like that, you might want to, and there are going to be differences.
Normally every time the vector xk.
So you might do something like yk equal to a xk minus 1, and then xk is equal to yk by some norm, maybe the L2 norm or the infinity norm or whatever. So you might want to normalize this so that it doesn't blow up, because you are, after all, computing a power summation out there, right? So you might have to do that. And this is, in our case, we didn't have to do it because our matrix had that structure. So everything was normalized. We started off with normalized x. So we made sure.
But here we did not.
Here we have it. We are looking at the specific, a generic algorithm. There we were looking at a specific case. So it was easier to avoid these kind of issues and just make sure that our inputs and the matrix maintain this structure, right? If it is scaling in some way, then you have to make sure that you normalize it over each of your iterations, okay? And you have to be more careful about with what the final eigenvector you get out as well. But that's sort of not the point. The question here is that if you did have some knowledge about the range of eigenvalues, then you can introduce a shift. So you would basically, instead of solving A, you're going to be solving A minus sigma I. But now you will see that this ratio can be lowered because you're reducing with this, because that means that this fraction can be made to be lower than what we started off with.
Okay.
Is it clear? Because this is what you're raising. So introducing a shift, which in the initial case seemed like a very simple thing to do, it's not really changing much. But when you're doing the power iteration, you can greatly increase this if your second eigenvalue is actually somewhat close to your original eigenvalue.
But you have to know how much to shift, right? Otherwise
Yes, exactly. So the thing is that to get the optimal solution, you have to, right? If you knew the second eigenvalue exactly, you would do that is the shift, and in one iteration you will converge, right? So power iteration will converge in a single step then, if you did the right shift. But in many cases, we might have a general notion about what the spectrum is like, right? And then you could do this. Okay? So this is just a trick, but it's something that will help you. Of course, whenever you do these kind of things, the shift must be added back to the result to obtain the correct eigenvalue of the original matrix, because now we are estimating for alpha minus sigma I. So you have to do that correction again. Is this clear? So now let's get to the next part, which is the inverse iteration. So if we are not interested in the largest eigenvalue, but are instead interested in the smallest eigenvalue, and I mentioned this briefly, you would do the power iteration now with A inverse, right? Because that's going to give you, it's going to give you lambda max, which is 1 over lambda min of the original, right? So this leads to an inverse iteration scheme, which looks kind of similar, and maybe compare it to that because normalization is much more important in this case, so I've written it in the normalized fashion. You see that in the original system, we had yk equal to axk minus 1. A comes on the other side here, which is basically like saying that A inverse, but I moved A out here. Now, of course, this is much more expensive to solve, right? Because you have to solve a linear system every time. In practice, what you would do is to factorize A into something like LU or something so that you can repeatedly solve this system of equations efficiently, okay? Again, if you think of doing something like the inverse power iteration, you will realize that the structure of the matrix A becomes very important. So the most common strategy would be to use some kind of a similarity transform, get a matrix B which has nice properties, something like a triangular matrix, because if this was triangular, then it's easy for me to solve this system, right? Because it's just a single sweep and I can do back substitution and solve all of it. So the combination of the inverse, rather the next stage I'll talk about in the next slide, where you're using the inverse power iteration with shifts, because that allows you to target specific eigenvalues. Okay. The inverse of it, so this is what I just mentioned, that you don't solve it explicitly, and so you're not incurring the cost of inverting A every single time you're doing this. Is this clear? Okay. So just a quick mention of this, which is the shifted inverse iteration. As before, you can use the shifting strategy to improve the convergence. It's the same idea. It's using it. This is the part which you should focus on. It's very important, is that it's also useful if you want to choose to compute an exact eigenvalue. Say, for example, in the case of the spectral bisection, we know that the smallest eigenvalue is, for a graph Laplacian, what is the smallest eigenvalue? Graph Laplacian, spectral bisection. Smallest eigenvalue, smallest eigenvector. The graph Laplacian is just going to be, for every node, it's going to be D and -1 everywhere else. Whatever. How many ever neighbors you have?
Oh, the smallest you need.
No. Smallest is 0. It's singular. Matrix is singular.
Oh.
The smallest eigenvalue is 0.
Yeah.
The smallest eigenvector is all ones.
One.
Remember we talked about
Yeah.
all ones? Because if you have this and you apply all ones, you're getting D adding up with -1s, which are all D again. So D minus D is equal to 0. So you're solving a system which is going to look like
one equation less. In some sense, we have one equation less.
right.
Yeah.
So 1 is the, here let's say 1 is the vector of all ones. So this is W1 and this is lambda1, right? We did this.
Yeah.
So now if you want the second one, you can do a shift, because I can choose some very small value, just about 0, and then do that shift. Now find the smallest eigenvalue at that
So
level.
once I find the small one, I'll just shift with the small.
There are better ways to do it. We'll get to it, but from the smaller side, you can do it with shifts. Because why? Is that if you want to compute the eigenvalue closest to some value beta, right? Since you will use beta as the shift, but the moment you use beta as the shift, the desired eigenvalue corresponds to the smallest eigenvalue. Because if you've shifted the spectrum by that much, that becomes your smallest eigenvalue now. And so the inverse power iteration is also useful when you want to target a specific eigenvalue. So this is the other part, which is deflation. So suppose that we have computed the largest and the smallest eigenvalue, right? And the corresponding eigenvectors. We want to get to the second, the third, and so on. And the most common way of doing that is to use deflation. Okay? I've mentioned this in some of the lectures, but basically you want to subtract the contribution of the eigenvector from this. And there are two or three different ways of doing this. One of the more popular ways, and this you should look in, is to use a specific matrix H, which is a non-singular matrix such that it satisfies hx equal to alpha E1, okay? E1 is just 1 and the rest all zeros. This is very similar. So there are several matrices. Sorry? Alpha is just some constant. Okay? It's just some fixed value there. And one example of this is a householder matrix. You don't need to worry. You can probably look at the second part or the second way to do it. I wanted to present this because in many of the SVD algorithms, this is what they do. What you can do is that you can compute a similarity matrix transform similar to this using this householder matrix, which is going to have this sort of a structure where you're going to have the dominant eigenvector or the eigenvalue at the diagonal out here, and you're going to be resulting with a big block diagonal matrix of size n minus 1 by n minus 1. And the eigenvalues of B now are going to be lambda n minus 1 all the way to lambda 1. So you are basically, by using a householder rotation, you have extracted the largest eigenvalue, and you're left with a matrix with all the remaining. Okay? Of course, you can repeat this repeatedly to get smaller and smaller matrices, and you can use the power matrix, power iteration to get the largest eigenvalues one by one. There is another way to look at it, and maybe this is a simpler way to consider the same thing, which is that assume that you define now a vector un, right, which has this property, which is basically that un transpose with the eigenvector basically gives you the eigenvalue, right? Then if I subtract the interaction between un and the primary eigenvector, right, then I'm left with a matrix where I have completely cancelled out the influence of the primary eigenvector. So the eigenvalues of A minus Wn un transpose, right, is going to have eigenvalues lambda n minus 1 to lambda 1 and 0, okay, assuming that it wasn't singular to start off with. There are some very simple choices for un in this case. You can choose un is equal to lambda n wn if A is symmetric and wn is normalized. So if you did this, then you will see that that condition would be satisfied, and then we would basically subtract wn transpose lambda n from A, right? Which is basically, you can think of it as the self-projection subtracted from A. And that's what you're extracting the influence of that particular dimension or that particular basis function out there. Of course, if A is not symmetric, and you will see that this is basically a sub-case of this, is that you will have to now find this other, the left eigenvector yn, which is of the transpose matrix. Of course, if A was symmetric, then yn is the same as wn, so we didn't have to do this. But basically, if A was not symmetric, you would compute the eigenvector, the dominant eigenvector of the transpose matrix, and use that to subtract out the influence. There is another more generic way of doing this. Without giving any proofs, I'm just going to explain that you can choose this vector by A transpose and the kth unit vector applied to it, which the k you obtain by taking the dominant eigenvector and normalizing with regards to the infinity norm and figuring out which of the kth, basically, which is the dominant row of your eigenvalue in our space. So you basically take that component and then you can self-intersect with that, and that will give you. So here are just some simple ways in which you could extract the influence of the dominant eigenvector.
How many times the last one is an approximation?
No, it's not an approximation.
It's an exact.
It is. It's not an approximation. It is going to take out the.
It's going to completely remove the.
Yes. To machine precision, yes. So it will, and that's why I gave it out here, because in many cases this is a nicer way to do it, because you can just completely just normalize the eigenvector, figure out the dominant direction, and extract it out. That's all you have to do. part. The QR part is going to give you your eigenvalues. And then you will recover. So if you get, it's going to reduce it to the triangular form.
Or
And
the triangular has the
values, and then you would go ahead and you would plug in and get the rest. Okay?
Is the remainder R diagonal in R is the eigenvalues?
No. No. The Q's are. The Q's are the eigenvectors.
The eigenvectors, right?
Yes.
They're not eigenvalues.
The diagonal of the,
Q is eigen.
no, not Q, the approximation A that you get.
Yeah, that has eigenvalues, yes.
No. So you start off with A, and you're progressively getting, this is no longer A. I'm calling it A, the AK as a
AK
K.
is actually the eigenvalue.
As it becomes triangular, the diagonal of that is going to be the eigenvalues.
And
So you,
Q can I call them vectors now?
so
When it's QK.
the cumulative effect. So if you keep a running product of all the Q's, that is going to converge to your eigenvectors. Okay. So the key thing for us to notice here is that the work per iteration is reduced from n cubed to n squared for general matrices and order n for symmetric matrices if we start off by reducing our matrix to a Hessenberg structure. That's the reason why you do it, because QR is too expensive otherwise. So this is the most common thing that you would see. Of course, what we are interested in, the expression we got out here. Okay. So once this summation where we were going through each of these values and we were computing this update out here. If H is tridiagonal, most of these terms vanish, which means that we don't need to have a loop out there. We just, so you can, instead of going all the way to 0, you can just say that I'm going to let it go sufficiently small and then I'm going to stop. Okay, that is a possibility as well. In many cases, depending on what you want, if you're interested in, say, the top 2 and the bottom 2 eigenvectors, eigenvalues, you will just let it run for 10 to 20 iterations. That's good enough. Again, this is just the same statement now said in a different way, is that if we let Lanchos run until k equal to n, the resulting tridiagonal matrix will be orthogonally similar to A. Of course, we are estimating this, right? So you could have rounding errors during this process of generating this orthogonal basis, that you would, the resulting system, because we are doing it one by one, and all we are doing is that numerically we are enforcing orthogonality to the already discovered basis. So rounding errors can cause a loss of orthogonality at this point. You can re-orthogonalize if it makes a difference, although again in practice you can ignore it because the resulting approximations are still reasonably good for what you want. And just to summarize, is that the biggest advantage of both Arnoldi and Lanchos is in their ability to produce good approximations to extreme eigenvalues for k much, much smaller than n. So we're talking of k equal to 20, 30. You will, for the most practical matrices, you're not looking at some bizarre pathological cases, but most matrices, you will get very, very good approximations, at least for the extreme eigenvalues. And those are of most interest to us. There are cases where you might be interested in the other parts of the spectrum, but in many cases, that's what we're interested in. Like I said, take page rank as an example and take spectral bisection as another example. That's what tells you. The other step, and I've again repeated this, is that they require only one matrix vector product, so they require very little auxiliary storage, and they're ideally suited for large sparse matrices. So the moment you have a large sparse matrix, this is in most cases your only choice, unless you want to do it in a sequential fashion. If eigenvalues are needed in the middle of the spectrum, say near some value sigma that you know, so you can compute the extreme eigenvalues and say that now I'm interested more in looking at a spectrum somewhere in the middle, so we can figure out what this sigma is and then look around it. Then you can apply both of these are iterative algorithms. You just need a matrix vector product, so this is just an additional correction onto this. And we can use this to solve it. Again, we are always assuming that we can solve the system some way. And that's how you would do it for the rest of the case. Okay? And